Hello, welcome back to Introduction to Genetics and Evolution. In the previous set of videos, we've been talking about deviations from Hardy-Weinberg, and particularly not in the last video, but the video before it, we looked at the measurement of FST and how you can measure differences between populations in allele frequencies. And what we saw in this case is you used the deficiency of heterozygotes to quantify a deviation from Hardy-Weinberg to look at these differences between populations. These differences between populations, as I emphasized both in the last video and the one before it, come from non-random mating. In this video, I'm going to talk about a different form of non-random mating, that of inbreeding, or mating preferentially with individuals more closely related to you than a random individual in the population. Now, differences in allele frequencies are often driven by patterns of gene flow or interbreeding. This is differences among populations. This is true when you're looking between populations, but it doesn't have to be true just between populations. But in fact, you can see something similar with patterns of non-random mating within populations as well. So the related concept, what we've talked about, is inbreeding. Now, this is, again, breeding between closely related individuals, such as siblings, cousins, things like that. And this often happens because the capacity for dispersal is often limited. That individuals can't just jump to someplace on the other side of the population, but they breed with individuals that happen to be physically proximate to them. Or to quote a famous song, they love the one they're with. Now, this changes the distribution of alleles among genotypes. So let's start by looking at an extreme form of inbreeding. This extreme form of inbreeding is that of self-fertilization, which is found in some plants. And they actually literally have their pollen is fertilizing their seeds. So let's imagine this population. We'll start at Hardy-Weinberg that you have 25% big A, 50% big A little a, 25% little a. What happens if this particular plant self-fertilizes, as you might see in the picture here? Well, the big A individuals will obviously produce more big A individuals because that's all they have. It's big A crossed to big A. Little a individuals will produce more little a individuals. But these ones, the heterozygotes, will make a spread. They'll make some big A individuals, they'll make some little a ones, and some big A ones. Right? So we take this 50% as it shows here, and a quarter of it goes to big A, a quarter of it goes to little a, and half of it stays within there. So if we're to look at the new genotype frequencies after one generation of self-fertilization, we see it becomes 25% big A plus 1/4 50% big A. So that comes out to 37.5% big A. Same on this side. And this one is 50% big A little a times 1/2, so it'd be 25% big A little a. So you can add these up now, it still adds up to 100%. But what do we see? We see, again, a reduction in heterozygotes relative to what we saw previously. Now we can iterate this over more and more generations. So now we have, again, fewer heterozygotes, more of these two homozygotes, until in the very long term, what do you expect? If you just keep self-fertilizing over and over again, what do you think will happen? That's right. The answer is you'll have all big A's or all little a's. That essentially, inbreeding, and particularly self-fertilization, but any form of inbreeding, eliminates heterozygotes. If you do it for a very long period of time, there will be no heterozygotes left. So every generation, the heterozygote fraction goes down, and you essentially create these pure breeding lines, big A, or little a. Now, how do we quantify inbreeding? Well, again, inbreeding, even if you're not looking at selfing, reduces the percent heterozygotes relative to Hardy-Weinberg or just Mendelian proportions. It feeds alleles into homozygotes. And again, this reduction can be used to quantify the extent of inbreeding that's happening in natural population. The measure we can use, and this is all going to look very familiar to you, the measure that we can use is Wright's inbreeding coefficient, which is often just abbreviated as F. F ranges from 0 to 1, where 0 is your at Hardy-Weinberg expectation for percent heterozygotes within the population. If you're between 0 and 1, you have somewhat fewer heterozygotes than predicted. And if you have an F of 1, it means you have no heterozygotes in the population at all. This sounds very familiar, doesn't it? It's very similar to FST. And again, F is calculated as the Hardy-Weinberg predicted 2pq minus the observed heterozygotes over the Hardy-Weinberg predicted 2pq. So let's do an example. Here's an example right here. Let's say you're studying a population that has this set of genotypes. So again, we use the same procedure we always use for calculating if something is at Hardy-Weinberg. We get the totals, the genotype frequencies, and the allele frequencies. So the total in this case is 1,000. Here's your genotype frequencies. Here's your allele frequencies, 0.7 and 0.3. From this, we see what the Hardy-Weinberg predicted genotype frequencies should be. In this case, we have 0.49, 0.42, 0.09. And look at that. Do we see if things are at Hardy-Weinberg or not? Here's the predicted percent heterozygotes. Here's the observed fraction of heterozygotes. And again, we have a deficit of the observed relative to the expected. So we just plug these numbers in. The expect is 0.42 minus the observed is 0.294 divided by 0.42, and our F in this case happens to be 0.3. That's pretty severe inbreeding. Let me give you one to try yourselves. These are genotypes from the Croatian islands. This is actually real data. I skipped the step for you of the genotype counts for you. I'm just going to go ahead and start with the genotype frequencies. Go ahead and give that a shot. Well, I hope that wasn't too difficult. Well, again, I started you off with the genotype frequencies. Let's go ahead and convert them to allele frequencies. There we go, 0.9 and 0.1. And from that, we calculate the expected heterozygote frequency. This would be 0.9 times 0.1 times 2, which would be 0.18. That is your 2pq. I'll write that in there just so you see it. 2pq is equal to 0.18. So this is our predicted. This is our observed. So our predicted minus observed over predicted. In this case, the estimated inbreeding coefficient for these Croatian islands is 0.04. Now you may be wondering, what is the difference between this inbreeding F and FST? Well, they're both based on fundamentally the same principle, right? They're seeing fewer heterozygotes than the Hardy-Weinberg prediction. They're both indicating patterns of non-random mating. One is indicating within two different populations that are individually at Hardy-Weinberg. The other is indicating behavior within a population. And they're both essentially the symptom of the Walland effect. Now, when you apply, this is where the difference comes in. You apply the inbreeding F when you know that you're looking at individuals within a single population, right? That as far as you can tell, these individuals can could freely interbreed with each other, but perhaps don't. When you apply FST is when you're quantifying a difference between populations. You're looking at individuals from here and individuals from way over there, and you're then trying to estimate, historically what has happened. How different are they in allele frequencies that you want to quantify? So how is this calculation used, and particularly the inbreeding F? Well, I have here just a couple of examples from some recent papers that were published. These are just their titles. You can look at the association between inbreeding and health or disease. Many of you know that inbreeding is often associated with health problems. So there's one here, inbreeding effects on fetal growth in Beirut, Lebanon. You can look at patterns of gene flow between, say, social classes to get sort of a societal implication to this. So this marriage within social or occupational class boundaries in Pakistan and how it affects inbreeding. And you can look at other cultural effects and patterns of breeding. So here's one from Spain, where they're looking at socioeconomic, demographic, and geographic influences. Patterns of inbreeding around the world differ, often associated with cultures. This shows the global distribution of marriages between couples that are related as either as second cousins or more closely related than second cousins. If you have a second cousin mating, then F would be on average 0.0156. And we see that there's some areas where you have a lot of marriages among related individuals. So as you see here in Saudi Arabia and Afghanistan, things like they see a lot. There are some areas where you see very, very little of it, such as, for example, in the United States, in Australia, in Russia, things like that. But again, inbreeding does happen, and it varies socially and culturally. Now, some of you may be thinking, isn't inbreeding bad? Haven't you heard of all this, like inbreeding depression and things like that? Well, in and of itself, inbreeding only changes the distribution of alleles among genotypes. Intrinsically, inbreeding doesn't cause a problem. It's only changing how alleles are distributed among the various genotypes. It does not make any alleles go away or turn bad. However, there is this phenomenon of inbreeding depression, and what this requires is natural selection as well as inbreeding. Now, the reason that inbreeding is often associated with this sort of depression is that populations often have many individually rare recessive mutations. We talked about this way back with our mutation lecture, right? That again, you have a few new detrimental mutations arising each generation. If they're recessive, as they often are, most bad mutations tend to be recessive, they don't really have any effect. But what starts happening, so imagine that they're rare and recessive, you're going to have very few homozygotes in the population. But what starts happening if you have related individuals mate? If you have related individuals mate and have kids, they're likely to have the same recessive mutation, right? And they're more likely to produce homozygous offspring. So this picture on the bottom might show you like individual genotypes across a population. And let's say that each of these red mutations is bad. Well, there's a bad D over here, there's a bad A over here, there's a bad D way over here, a bad E over here, a bad B there. It's very unlikely. Pretty much these people could all mate with each other, and there's only one combination here among all these individuals that would actually produce a problem, right, if they're all recessive. And that would be if this individual right here interbred with this individual right there. In contrast, if they're breeding, let's say, for example, they're self-fertilizing or breeding with their sisters or cousins, then you're much more likely to accidentally run into somebody who has that same bad mutation, and therefore to actually have this mutation effect show up because you're making it homozygous. That's why you have inbreeding depression. It's this combination of inbreeding plus rare recessive mutations. We see effects of this often associated with dog breeds and the inbreeding associated with making them. That we're breeding relatives to make these various dog breeds, right? We're trying to essentially pick the desirable qualities we like, their behavior or the way they look or something like that. In doing that, when breeding individuals that are related to each other, we end up increasing the inbreeding coefficient. And in fact, inbreeding coefficient in some dogs can be as high as 0.5. That's unusual, but some of them do go that high. In fact, there's some poodle varieties that have an F of 0.7. That is huge. I mean, at this point, you're seeing almost no heterozygous retained within there. And a UPenn study showed that 75% of puppies that have an F greater than 0.67 die within 10 days. So there's a huge detrimental effect associated with this. Some of the effects that have been documented are, for example, in King Charles Spaniels, they get this, I don't know how you pronounce it, syringomyelia. Essentially, the dog's skull is too small for its brain. Causes, as you can imagine, all sorts of problems. But here are several others. Boxers tend to get high epilepsy. Pugs have breathing problems. Bulldogs can't mate or give birth unassisted. Some of them, not obviously all of them. Mastiffs, St. Bernards, and Great Danes. This is a very common one. Hip dysplasia. Hip dysplasia has been studied quite a bit in a couple of contexts, such as the Icelandic sheepdogs. Let me show you some data about that. Here is the association of incidence of hip dysplasia with inbreeding. So on the y-axis here, we have percent of individuals having hip dysplasia. On the x-axis, we have inbreeding coefficient, right, associated with them. And what we see here is we see a greater and greater incidence of hip dysplasia associated with more and more inbreeding. Again, the problem here is you are making recessive mutations homozygous. By making them homozygous, you're making their bad effect visible in the individual. That's what causes inbreeding depression. That's why one of the reasons we're interested in it. Thank you so much for your time.